we are now equipped to deal with the law of large numbers and a fair amount of generality. We begin with what the inequality of Chebyshev says in the case of a sum of independent variables. So, let's take stock. Chebyshev's inequality says that for a generic chance variable x, the probability that the absolute deviation of x from its expected value exceeding any given number tau is bounded above by the ratio of the variance of x to tau squared. Now bear in mind that this is true for any chance variable x. In particular, what if we replace x by Sn? Then all we'll have to do in Chebyshev's inequality is strike out sundry references to x and replace them all by S sub n, and we've got now a version of the inequality for a partial sum of independent copies of x. Now let's focus on this. This says something about the probability of the absolute deviation of Sn from its expected value. And here is where additivity comes in triumphantly. Okay. So let's take stock of what the key issues are. So to begin, we are starting with repeated independent trials. A chance variable x with expectation mu, variance sigma squared, and x1, x2, x3, and so forth are independent copies of x. We form partial sums, Sn being the nth of these sums, being the sum of the first n coordinate variables. And the moment we have a sum, additivity comes into play. To begin, expectation is additive without qualification, and therefore the expectation of Sn is just n times mu. And since the summands are independent, variance also is additive, and so the variance of Sn is n times sigma squared. It is important to keep in mind that the variance connotes an expected squared spread around the center. The actual spread, therefore, is captured by the square root of the variance or the standard deviation. And so what can we say about the standard deviation of Sn? It is exactly the square root of n times sigma. Now observe that both the expectation and the standard deviation increase unboundedly as n increases. But it is important here to keep an idea on the proper scale. The expectation increases linearly with n. The standard deviation or spread around the expected value increases only as a square root of n. And this has got very important consequences. Consider, for instance, when n is 100. The expectation of S100 is 100 times the expectation of one variable. But the variance of S100 is also 100 times the variance. The standard deviation is only square root of 100 times the standard deviation, or 10 times sigma. So the expected value has moved by 100, but the spread has only increased tenfold. What if n is 10,000? Then the expected value has moved 10,000 steps. The spread has only increased 100-fold. And this suggests that we're getting an increasing concentration right around the center. The spread around the center is increasing much slower than the rate of movement of the expectation. Okay. So let's focus on this, and now immediately try to write down a probability for a deviation from a mean. Remember, our estimate for the mean, the expectation, is Sn over n. And what we would like to know is, what are the chances that Sn over n deviates in absolute value from mu by even a tiny amount, epsilon? Okay. Now the first thing we should do is simplify the fractions by clearing the denominator. Multiply throughout by n, and the event that Sn over n minus mu in absolute value exceeds epsilon is exactly the same as the event that Sn minus n mu in absolute value exceeds n times epsilon. Now focus on the right-hand side. The term n times mu is exactly the expectation of Sn by additivity. And we may identify the term n epsilon with the deviation parameter tau in Chebyshev's inequality. And so we just write down the answer. This is bounded about by Chebyshev's inequality by the ratio of the variance of Sn to tau squared, but tau is n times epsilon, so we get n epsilon the whole squared. Additivity of variance, because the summands are independent, says the numerator is n times sigma squared. And we find that there is a factor n in common in numerator and denominator. Cancel that, and we've got an elegant and simple expression. Let's focus on this inequality. It is difficult to ask for something much simpler and compact than this. The probability that an absolute value, Sn over n, deviates from mu by as small an amount as epsilon or more, is bounded about by sigma squared divided by n epsilon squared. Now, sigma squared is the variance of the underlying chance experiment. Epsilon squared is your fixed error parameter squared. These are fixed constants in your application. Remember, we are looking at a whole sequence of partial sums. What happens to the right-hand side as n becomes larger and larger and larger? Well, eventually, the right-hand side tends to 0. And this is the content of the weak law of large numbers. So we start with a sequence of independent repeated trials, where each trial has got an expectation mu, variance sigma squared. Epsilon is your tiny fixed deviation parameter, your allowable error tolerance. We form partial sums. And the weak law of large numbers says that these partial sums are increasingly concentrated at mu in the following sense. That Sn over n deviates from mu by even a tiny amount, with a probability that goes to 0 as n becomes larger and larger and larger. Of course, we should conclude this with a nice little slogan, a pithy slogan, which captures the essence of this mathematically precise statement. And here it is. The probability that Sn over n deviates from its expected value mu by even a tiny amount is small, provided only that the sample size n is large enough. Or another way of saying this is, in a probabilistic sense, Sn divided by n is a good estimate of mu. Does that look familiar? Of course it does. Right? This is exactly the passage we went through when we tried to defend why sample means were good estimates of population proportions in a poll. But now, of course, we have it much more generally.